Now that we have spoken much about the flow boundary conditions for fluid, let's have a look at the non-flow boundaries, especially for walls. So when I'm specifying the boundary conditions for a wall, when I double click or I click on edit icon for a wall type of boundary, I have options for different kinds of models. Let's say I start with the momentum boundary condition for a wall. What you can see here is that it also displays the adjacent cell zone to a wall. This is very helpful because sometimes you might have a wall which is being shared by two different cell zones. In that case, Fluent automatically creates a shadow zone. I'll speak about this in a minute. But the adjacent cell zone is very helpful to know where this wall is acting as a wall for, which fluid domain it is encompassing. So usually in the momentum conditions, we have specifications for the wall motion. We have to specify what are the shear conditions. So usually wall motion, if it's a stationary wall, this is the usual case. If it's a moving wall, let's say a conveyor belt, or let's say it's a stirrer which is stirring inside the domain, or let's say the walls of a cylindrical container are rotating around the axis, and we want to see how the free surface is behaving in such cases. So you can also specify a moving wall kind of a boundary. And the shear conditions are basically the no slip boundary, or we can also specify the shear value, and we can give a value of either 0, which means it's a free slip wall, or it can be also you can also specify your own shear stress value. By the way, this free slip wall is when we specify the specified shear to be 0. This is helpful if we are trying to model the interface between a liquid and a gas, where we don't want to do a multi-phase analysis, but we want to see the effects of a zero shear wall at the interface between the liquid and gas. Additionally, because of turbulence modeling features, we can also include the wall roughness. This is only helpful if you are doing a near wall treatment while using the turbulence models. If there is no turbulence model, it's a laminar flow, then this wall roughness input is redundant. But additionally, apart from the momentum boundary conditions, the other kind of boundary is because of the thermal boundary conditions. Now, there are a variety of ways in which the thermal boundary conditions can be specified. If you are a bit familiar with what are the different ways in which you can close or you can give constraints to a differential equation, you might have come across something called the Dirichlet boundary condition or the Neumann boundary condition. The Dirichlet boundary condition specifies the value of the quantity being solved for. So in this case, if it's an energy equation, we give the value of the temperature at this surface. That's the Dirichlet boundary condition. That's one possibility. We can click on this icon, we can activate this, and then we can specify the temperature in any unit that you're comfortable with, which you use for your case. But we can also give the gradient of the temperature, which is basically a flux. So you can give the heat flux, that is watt per meter square, which can also be specified as a boundary. That's a Neumann boundary. Then you have some mixed boundary conditions. For example, you have the convection boundary condition, in which you specify the heat transfer coefficient of the free stream. So you're not modeling the domain beyond the wall of the domain, but we are saying, okay, outside the ambient temperature is, let's say, 25 degrees Celsius, and this is the specified heat transfer coefficient, and in that case that much amount of heat transfer is also included into the problem. We can also include the radiation effects. Let's say there is a radiating surface outside, its external temperature is specified, and also the external emissivity is specified for that wall. So accordingly, the radiation effects can also be included. And the corresponding effects travel into the domain from this wall. And we can also have a mixed boundary condition, combination of convection and radiation for such purposes. Now, Fluent also allows us to use a feature by which we can model heat transfer within the wall without actually meshing the wall. Now, this is especially helpful if without meshing the walls, which are very thin walls, because if you have a very thin wall, what happens is the overall aspect ratio of the mesh which is generated inside is very bad, and the cell count increases inside the domain if the same aspect ratios have to be maintained and the smooth transition is to be maintained. So what we usually try is that we don't try to mesh such walls, but we can use either a 1D heat conduction across the wall, in which case we can specify the wall thickness thickness, and in case, let's say, there is also heat generation rate inside the wall thickness, in that case that value can also be specified. And we can include the material property of the solid domain, which you can include into the case first of all from the materials panel for the solid, and we can assign that material for the wall. This is very helpful in such situations when we don't want to model the thickness of the wall or the heat transfer within the wall, but we want to see the effect inside. Fluent additionally also gives the possibility to use something called the shell conduction model, in which it's not just 1D heat conduction which is included, but also a transverse heat conduction along the wall through the shell conduction model is also included. So this is very helpful. So Fluent generates some additional cells in this case internally, which are not available for post-processing, but overall you can see, or we can get the effect of transverse heat conduction, not just in one direction but also in the transverse direction, because of which the appropriate conjugate heat transfer analysis can be performed. So in this way you can activate the shell conduction model. I can activate the shell conduction. So in that case also the transverse heat conduction is included. Two-sided walls are the other class of problems which we often encounter. It can be a case that we have uh, a, um, a phase zone on which both sides, either there is a fluid domain or a solid domain and a fluid domain. In such cases there is a wall which is being shared by two different cell zones. So in such situations Fluent automatically creates a shadow wall zone when you include that mesh into your domain. And the two-sided walls may be coupled, that is, heat from one cell zone can get transferred to the other cell zone through the wall, or in other cases we can also make them uncoupled. So we're going to look at both cases, and we can also give appropriate thicknesses. We can do shell conduction modeling as well. Um, so if you want to make them uncoupled, you can specify your own specific temperature as well, and this is also a very good feature, that you want to actually do two different simulations where you don't want the heat from one domain to pass on to the other, and we want to do separately their simulations. So this is very well also possible, but usually doesn't make very good sense. We would usually prefer a coupled kind of a wall. The other kind of boundary, which is non-flow boundary, is a symmetry boundary. So what it means is it's like a zero shear slip wall in viscous flows, but it also means that even thermal solutions all are reflected across the surface. There is no extra input which is required. The only task we have usually is to identify what is that symmetry boundary. So we only need to define the symmetry properly, and I'll just give you some ideas about it. Let's look at this example. It's a complete rectangular cross-sectional duct that we are having, and we can take 1/4 section of it. We can assign this and this vertical plane and this horizontal plane to be symmetry faces, and then we are actually modeling 1/4 of the overall model. Now this is fine. If the flow is occurring primarily in the axial direction, then this kind of boundary assumption, symmetry boundary assumption, is quite good actually. We'll see where else it's possible. So we can also have, let's say, flow going through a cylindrical pipe. In that case we can take a 90-degree sector. If the flow is primarily axial, in that case we can take this 1/4 of the overall cylinder and do apply appropriate symmetry boundary conditions to perform efficient simulations. We can reduce the cell count immensely in such cases. But let's look at examples where it is not possible to use a symmetry boundary. Now that's a typical case. It's a situation where we have fluid going into a domain, and because of natural convection effects where the gravity effects have been activated, then we cannot treat this mid-surface as a symmetry boundary, because then it would mean that the gravity is going from both sides towards the symmetry surface, which is not physically the right interpretation. So in such cases this is not a symmetry plane. In other cases it can be because of physics that we cannot apply the symmetry boundary, or it can also be because of geometrical considerations. Let's say the geometry was quite different in that case, on the top and bottom. In that case, even if gravity is not activated, we cannot include a symmetry boundary at the middle. Still another possibility of a physics where symmetry boundary may not hold is for Coanda effect. If you want to capture Coanda effect of a jet moving in around a free stream stagnant fluid, in that case this jet becomes unstable and it tends to move towards one of the surfaces. This Coanda effect will be completely missed out if we take a symmetry boundary. So such cases we cannot really create a symmetry boundary because the physics is not symmetric. This is another example where the flow is always crossing or swirling inside this circular cross-sectional cylinder, let's say. So in that case, it's not a plane of symmetry either, because flow is not reflecting across the surface, but it is crossing across. So in such cases, it's rather helpful to use a periodic boundary. So periodic boundary is the other possibility by which you can reduce the problem complexity. So in this case, the swirling effects makes it impossible to use it as a symmetry plane at the middle. Let's move on to the cell zone conditions. We'll see this briefly for the fluid cell zone and solid cell zone, and we'll have some concluding remarks. Cell zone conditions for fluid zones, there are some new features which have come up in ANSYS Fluent 13. If you are familiar with the previous GUI, you might have to find your way in the release 13 now, because there are some new features which have come up. Usually the only required input is only the fluid material, but you can also include some source terms or sink terms as constant or user defined functions for the different equations. So this can be done through activating the source term here and then going to the appropriate tab here for source terms. You can also fix values. You can also make the flow specifically in some regions, let's say a porous medium porous region, you can make the flow to be laminar. This is also possible. So it can be, there are a variety of options available. And in case, let's say we want to do a frame motion, let's say we want to model a multiple reference frame, there's a rotating domain and there is a stationary domain. For turbo machinery applications, we can also activate the frame motion and give the specific inputs. Now what is included in ANSYS release 13 is a new feature in which the frame and mesh motions can be defined with respect to either the absolute frame or with respect to also the relative frames. Now this is very interesting because you can have 2 degrees of freedom of a rotating turbine, and there can be rotation around 2 axes, both of which can be included. This is a new feature which has been included as a full-fledged feature in ANSYS Fluent Release 13. As far as solid zone conditions are concerned, again, it includes, usually we do not have a fluid flowing inside a solid zone. We only have things for the heat conduction problem being solved. So it's without the advection term in the energy equation, it's or the convection term. It's primarily the transient and the diffusion term, and if we want to include, we can also include a source term for a heat production inside the solid domain. We can also give a domain motion to it. What is interesting in this case is that for such zones, we can specify the material as we wish. We can include it into the domain, and we can give the specific inputs for the material type as well. So one interesting thing you might come across often is when we are dealing with, as CFD engineers, we are modeling systems. So we are trying to fool, let's say, the software sometimes. So software offers us something called the solid zone, and this can be very well used to model vacuum. Or let's say we have a stagnant air. We don't want to model the advection terms variation. We are not interested in the velocity variation inside a domain. So we can very well treat it as a solid domain and give it the properties of, let's say, air or vacuum at very low pressure. So for modeling such things also, when there is no convection taking place, you can simply treat that fluid domain as a vacuum material also. So we can treat such a fluid domain as a vacuum material by considering it to be a solid domain where we don't want to include the convection effects. So just to summarize, basically it's the boundary conditions and the cell zone conditions which ensure that you have a unique solution inside your domain, and ANSYS Fluent offers you a variety of options to specify these boundary and cell zone conditions. A good understanding of fluid mechanics and CFD based equations which are used to solve the flow equations is very helpful to understand the different inputs, and it's more about experience which will teach you how to give the appropriate inputs in terms of for compressible or incompressible flows, which kind of boundary you should use, and it's also based on experience what results you have from the experiments, so that you can uniquely define your problem. So I hope you could follow concerning how to set up a problem as far as its boundary conditions are concerned. This concludes the lecture as far as the problem setup of any given CFD problem is concerned. What we still need to cover is the solver mathematics part and to do a little bit of post-processing. So I hope you are in a position now that you can start setting up problems, start defining your project up to the level that it's just the numerics which is hindering you from simulating your problem. Thank you for your attention.